Okay, here we are. And in this little conversation, we're going to be talking about converting coordinates. We're going to convert from polar to rectangular and from rectangular back to polar. And I've pre-written some notes here for you. These are, I don't know, sort of the formulas that we're going to use, in order to convert from rectangular to polar. And then on the right-hand side of your screen, we see that we'll be converting from polar. It looks like P-O-L-E-R, but that's an A, I promise. From polar to rectangular. And you don't have to write these down right now, but I wrote them here because we're going to use them. And then after we use them, then these pre-printable or these printable notes, these sort of fill-in-the-blank notes, there is a spot for us to write these in, but they come sort of after we've already used them, which is a little strange. But anyway, here they are. Let's just look at these for a moment. The conversion from rectangular to polar, none of this is very difficult, okay? To calculate the r value, if we're given an xy coordinate, or xy coordinates for a point, we will calculate the r value by adding the squares of our x and y coordinates, and then we do need to take the square root of those, so that's basically the distance formula. And to calculate theta, if our original angle measure is in the first or fourth quadrant, then theta will simply be equal to the inverse tan of y over x, the y coordinate divided by the x coordinate. If our theta value is in quadrants 2 or 3, we'll have to still take the inverse tan of y over x, but remember that the range of the inverse tangent function is only going to output an angle measure in the first or fourth quadrants. So that's why we will have to take and add pi over 2 in order to make sure that our theta value, that's Sophie's tail, of course, swatting me in the face. We'll have to add the pi over 2 in order to sort of swing the hypotenuse or the radius or whatever you want to call it into the correct quadrant. And then from polar to rectangular is easy, right? Just drop your r value in there, take the cosine of theta, do a little multiplication, and you'll be able to quickly calculate your x and y values. Sophie, why are you biting me and scratching me? Ow. That's not nice. I feed her, and what does she do? She bites me. Better not bite my head. Just be cute. Now you're purring. You're so strange. All right, so let's see if we can find some rectangular coordinates of some points. Another recommendation that I have for you is, not for you, you're just a pest. Get out of here. Ow, ow, ow. She's small, but her teeth are sharp. So here we're given rectangular coordinates, and I can tell that because I see the pi over 6, so that's a theta value clearly. And you can use these formulas for sure. Or you could do what I've done in so many videos, is draw a picture. Plot this point. Where is 2 comma pi over 6? So I'm going to do this one both ways. For starters, let's use the formulas. All I did was take the r value of 2 and the theta value of pi over 6 and plug it into those two equations that you see in the top right corner of your screen. And now we need to evaluate cosine and sine. So that's 2 times cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. So our x coordinate is the square root of 3, and our y coordinate is a 1. So we can say that x comma y is equal to root 3 comma 1. And that is the point that we would plot. The alternative is, and I'm going to sort of scribble out the one that's below this because I don't want to do that one. Your alternative is to draw yourself a little picture. We know that pi over 6 is just a little ways into the first quadrant. We have a radius, in other words, a hypotenuse of 2, which is very sort of fitting because in all of my videos, pretty much, I use a hypotenuse of 2 when I'm evaluating my trig functions. And we know that pi over 6, which is our reference angle, is a 30-degree angle, which means that the side opposite that angle is half of the hypotenuse, which in this case is half of 2, which makes it a 1, which means that the long leg is the square root of 3. I don't need to belabor that because you know that information all too well. And so what are the coordinates of this point that are out here at the end of the hypotenuse? In the x direction, we have moved away from the origin a distance of root 3. In the y direction, we have come up a distance of 1. Sounds like root 3 comma 1 to me. Ugh, terrible. So a couple of different ways to get yourself a final answer, which in this case is a point using rectangular coordinates x comma y. Exact same process on this one. In this particular case, I think that drawing a diagram is a really great idea because 3 pi over 2 is south or down. So if we're aiming at 3 pi over 2, and we take 6 steps backwards, we end up here. And this is a distance of 6. I think just from the diagram, you can probably tell me what the coordinates of that point are. So the answer on that one is 0, 6. You may go through the process of using the formulas, x equals r cosine theta and y equals r sine theta, and make sure that you come up with those same coordinates. And now let's convert from rectangular to polar. So again, these are rectangular coordinates. You are welcome to start out by drawing a diagram. I'm a big proponent of that, and especially I think for converting rectangular to polar, I'm going to highly recommend that you draw just a quick sketch. So let's draw a little picture here. Negative in the x direction, positive in the y direction. That's putting us in the second quadrant. We've come to the left, 2 root 3, up 2, so maybe we're here somewhere. And this is negative 2 root 3. And this is a distance of 2. If you wanted to, you could turn this into a triangle and label your side lengths with a 2 and a 2 root 3, but it should be negative. So however you want to draw your diagram, but there we go, and that's fairly accurate. Now let's see about using these formulas. In order to find our r value, r is equal to the square root of x squared plus y squared, which in this problem is equal to the square root of negative 2 root 3 squared plus 2 squared, which is equal to the square root of negative 2 times negative 2 is 4. Root 3 times root 3 is equal to 3. 4 times 3 is equal to 12. And 2 squared is equal to 4. 12 plus 4 is 16. Square root of 16 is 4. So we have our radius. I'm not putting in a box around it because it's not really our final answer. It's only a component of our final answer. The other thing that we need is our theta value. And remember that our theta value on the diagram is over here. It's that entire distance, or I shouldn't say distance, it's that entire amount of rotation that swings us from the positive x-axis, or the polar axis in a moment, around into the second quadrant. Theta is equal to the inverse tan of y over x, that's opposite over adjacent, which in this problem is equal to the inverse tan of our y value is a 2, our x value is negative 2 root 3, and that is equal to, I'm going to put my calculator in degree mode, because if you put your calculator in radian mode and you get an answer, the answer is going to be potentially a really lousy looking decimal that's not going to mean a lot to you. I suppose if it's less than 3.14, then you know it's a radian measure that's putting you somewhere between the first and second quadrant. If it's a theta value that's, or a radian measure that's negative some amount, anyway, it'd be tough to tell. Degrees, it's just so easier to tell where it's trying to put you. So I'm going to use my TI, what is this thing? Oh yeah, the TI-30XA single line input scientific calculator. We'll turn it on, and I'm already in degree mode, but if I needed to change it, I can hit the DRG button in the top row and just keep cycling through, looking at my screen until I get the DEG on my screen. I will type in, now this is a little bit tricky. I'm going to type 2 divided by, and then above the number 8 there's a parenthesis. I'm going to hit the parenthesis, and even on my screen it puts a little set of parentheses up there in the top right corner. And now I will type 2 times 3 square root, and now on my screen I see 1.732. That's the square root of 3. Hopefully, when I hit the close parenthesis button above the number 9, it's going to do the multiplication of the 2 times the rad 3. And it did. I got 3.46. All right, now I'm going to hit equals, and hopefully it will take the number 2 and divide it by this terrible decimal on my screen. And I got 0.577, which I think is correct. However, it's a positive number, but I need to make it negative because my denominator was supposed to be negative. So down here by my equal sign, there's a little plus minus button. If I hit that once, it puts a negative sign to the left of my decimal that's on the screen. I'm going to leave that decimal there, and now we need to take the inverse tangent of that. So I hit the second button in the top left corner, and then I'll hit the tangent button, and I get negative 30. All of that for a negative 30. So I'm going to write down negative 30 degrees. Now, where is negative 30 degrees? Negative 30 should be starting us aiming in the direction of 0, which is to the right, and rotating us down 30 degrees into the fourth quadrant. But if you look at your diagram, you'll notice that you're not supposed to be in the fourth quadrant. You're supposed to be in the second quadrant. So this is one of those examples where, is my iPad freezing? No, here we go. This is one of those examples where if your theta value is supposed to be in the second or the third quadrant, then after you take the inverse tan, you're going to have to add a half of a rotation in order to swing the angle measure into the appropriate quadrant. So let's go back down. We've been operating in degrees so far just now, so let's, you could write yourself a little note, but that's in 4. Add 180 to get to quadrant 2. Negative 30 degrees plus 180 degrees is equal to positive 150 degrees. That works. Or positive 150 degrees if you use the multiplier in order to make the conversion. Or if you can tell that 150 is 30 degrees short of 180. So in the second quadrant there, what we're really working with is a reference angle of pi over 6, which means that your theta value is actually 5 pi over 6. You're welcome to, if your mind works that way, just make the conversion sort of in your head by referencing the diagram. I'll write down 5 pi over 6. And then we can finally express our final answer, our solution, which is a polar point, r comma theta, which is equal to 4 comma either 150 degrees or 5 pi over 6 radians. Not difficult, okay? It's a little detailed. There's a little arithmetic. Could you do all of this with a 4-function calculator? The first half of it, mostly. The second half with the inverse tan, not so much. However, could many of us have answered this problem simply by drawing the diagram, seeing the relationship between the side lengths, that the short leg is equal to, that if you take the short leg of this triangle, which is a 2, and you multiply it by rad 3, you would get 2 rad 3, which is the length of the long leg. Therefore, this is a 30, 60, 90 triangle, and you sort of go from there. Pythagorean theorem gives you the hypotenuse, but the fact that it's a 30, 60, 90 triangle could definitely allow you to figure out that theta value without using a calculator, just using your knowledge of the 30, 60, 90 triangle. Would I ever give my students a problem like this and not allow them to use anything other than a 4-function calculator? Absolutely. I would totally do that. And if you're not one of my students, my bet is that you have a pre-calc teacher or a trig teacher who might just do that to you also. So make sure that you're prepared, or ask whether or not you're going to be allowed to use a 4-function scientific or graphing calculator on quizzes or tests where you're being evaluated or assessed on this information. 0, -6, you can plot that point. I guess I could do this one. This is a pretty quick one. 0, -6, that's x comma y, 1, 2, 3, 4, 5, 6. So we're down here. This is our point. And we need polar coordinates for that. I would recommend using a positive r value of 6, since the point is 6 units away from the pole, otherwise known as the origin. And in what direction are we aiming in order to go from the pole down to that point? You need to go down. You could use 270 degrees. You could use 3 pi over 2 radians. You could use -90 degrees, negative pi over 2 radians. Any one of those 4 options for an angle measure would work. I'm going to use 3 pi over 2. That was so easy. In the previous problem, it took us like 7 minutes or something. I don't even know how long it took. And we did all this arithmetic and blah, 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 and inverse tan. And then we just did this problem in like 30 seconds. See the power of the diagram and of knowing the various relationships and angle measures and your degrees and your radians and your triangles. And if you know those things, it makes doing some of these problems a lot easier. So the final answer for that second example would be 6 comma 3 pi over 2 or 6 comma 270. And I'm going to call it here for this segment of the video. And I invite you to join me for the next segment. All you have to do is click on the link right below me, and it will take you to a conversation about converting equations. So we're going to convert rectangular to polar equations first, as you can see, and then I'll do a couple examples of converting from polar back to rectangular. Hope to see you there. Thanks so much.